Technology whose roots can be traced all the way back to 12th century China. And although the technology has advanced beyond recognition, with the guns growing in size and power, their ammunition has evolved from spherical to the more familiar bullet shape to make them more efficient at supersonic speeds. The barrels have been bored with twists to impart a spin on the round to make it more accurate. And the method of their transportation has revolutionized how they're used. But there has been one constant for this technology through the centuries. Today we're going to learn how this technology looks set to be revolutionized by its largest iteration to date with the invention of the railgun. Railguns are guns that use electromagnetic force to propel a projectile instead of an explosive. Using explosives to power artillery has some drawbacks. Perhaps the most glaring one being that naval ships have to carry huge caches of explosives on board to power their guns. This has backfired several times throughout history, particularly during World War II, when on multiple occasions Japanese attacks detonated huge stores of ammunition within ships, with the most horrifying case being the kamikaze attack on the USS John Burke, where the resulting explosion dwarfed the gigantic ships in its convoy. Obviously, avoiding future cases of this would be ideal, but this isn't the only advantage. Current railgun designs are doubling the muzzle velocity of all naval artillery with hypersonic speeds up to Mach 6. Most naval artillery max out at Mach 3. This would extend the range and reduce the time to impact by nearly double too, if it wasn't for the elevated air resistance at these speeds. This technology has been a focus of the US military for decades, and for good reason. So let's see how it works and what needs to improve before we see it introduced to service. Railguns use electromagnetism to propel a conductive armature housing the projectile downrange. The physics is quite simple, however the math is not. Two parallel rods are connected to a power source, and these two rods can be considered the weapon's barrel. Connecting these two rods and completing the circuit is the armature. As the current passes through the rails, it generates a magnetic field. The same happens as it passes through the armature. The interaction of these perpendicular currents through the magnetic field produces something called the Lorentz force. This force acts both perpendicular to the flow of the current and the magnetic field. In the case of the railgun, this force is what pushes the projectile through the barrel and downrange. The beauty of the Lorentz force is that it's consistent, meaning the longer the barrel, the higher the muzzle velocity. But the power required to simply overcome the static friction within the barrel of a miniature railgun can require significant amounts of energy most individuals don't easily have access to. This is when things start to get extremely interesting or extremely challenging, because both solving for the Lorentz force and generating sufficient Lorentz force are both huge engineering challenges that have only been made possible and sustainable in the last 20 years. The Lorentz force in the case of a railgun is simply the current multiplied by the armature width, the magnetic field in Teslas, and sine theta, where theta is the angle of the current, which in this case is 90 degrees. The magnetic field B is a property of the railgun's design, such as materials, rail separation and diameter, and overall design geometry. With some assumptions, the equations clean up a bit, but for actual railgun design, these assumptions can't be made. While this technology has huge potential, there are some problems that need to be overcome to make this a serious weapon system. First and foremost, the same force that is applied to the armature also acts on the parallel rails. Quite literally, every time the weapon system is fired, the gun is actively trying to tear itself apart. On top of all this, the heat generated during each shot is so immense it is melting the rails. This can be seen during test fire drills with prototype railgun systems. That discharge you see behind the projectile is not the result of explosive propulsion, but a result of the resistive electric heating created by the huge current running through the rails and the frictional force between the armature and the rail, causing the rails to melt and shed material during each shot, causing more damage to the rail. These are unavoidable side effects, which are currently limiting the railgun to just a few shots before the damage breaks the gun entirely. Next, and possibly the most obvious limitation to the railgun design as a whole, is power. For this weapon to ever be introduced to service, it would have to be paired with a power source capable of providing the 25 megawatts needed to fire it. Even if previous generation ships had this capability, they would not have had enough power in reserve after satisfying the needs to the onboard systems and propulsion. But America's new futuristic Zumwalt-class destroyer is an all-electric composite ship that was slated to test this new weapon, with a generator capable of creating 78 megawatts. It would still have 58 megawatts of capacity available after providing for the rest of the ship's essential power requirements. Difficulties in railgun development and fiscal pullbacks in Zumwalt construction have delayed their introduction, but they can and likely will be retrofitted in the coming years, once the current durability problems have been solved. And while this technology is currently being funded by the military, it has far-reaching potential for other industries. We spoke recently of the challenges of intercepting ICBMs with traditional missiles. Railguns could allow multiple interceptors to be quickly fired at a fraction of the cost and increase the chances of success. They have even been suggested as a means of protecting the Earth from asteroids, with huge versions in orbit to destroy or change the direction of incoming asteroids. Launching a satellite like this could also be made drastically cheaper too, if we can deliver the materials to orbit with nothing more than the force a magnetic field imparts on a moving electric charge.